Okay, let's get going here. Everyone doing okay? These weeks are just cranking by. We have our midterm on the 6th of March, right? And that's 2 weeks from today, if I'm not mistaken. Let me double check that. Yep, is that 2 weeks? Yeah, that's 2 weeks from today. And just FYI, that day I will not be here, so there will be a proctor giving the test. So just so you know, I don't want you to walk in and be freaking out. So yeah, all right. So let's continue on here. We're going 11.5 chain rule. So we all remember the chain rule, right? From Cal 1. It was when you're learning it, I think the chain rule is the most difficult to get. That's my opinion, right? Product rule, quotient rule, all that stuff. But chain rule was the one where you really had to understand composition of functions. What we're going to do is we're going to extend this idea of the chain rule into functions of several variables, which is what we started looking at, like f of x, y, right? So how does the chain rule work here? So let's start with the first example. This is something that we have already seen, all right? So this is Cal 1, and there's actually no chain rule here at all. It's just the derivative. So if we're asked to find dy dx of this, no problem, right? 2x plus 6, we're done. We're happy, right? And this is an equation that represents the slope of the tangent line. If you give me some point x, some x coordinate, this will be the slope of the tangent line on that curve, right? What I want you to understand, though, I guess that what's going to help us today kind of understand what's going on here is that when you look at y as being a function of x, so y is some function of only one variable, then when we talk about dy dx, this is a ratio. It's basically saying how much does the y coordinate change if the x coordinate changes just a little bit. So back, with the graph of this, that's a parabola or something like that. So we're saying if we have x here, we have some point, then if we just change x a little bit, let's say move x to the right just slightly, then our point's going to move, right? And when our point moves, we want to know, like this was where it started, okay? That was where it was at x. So when I move to the right here, how much is that going to change, right? And so if we take the ratio of this change over this change, that is what the derivative is, like rise over run. So one variable changes a little bit, x, and we're trying to figure out how that impacts the y. All right, now, visually, I doubt you've ever seen the derivative, maybe you have, like this, presented like this. If you have y as a function of x, y can be determined if x is known, right? That's obvious. If x is known, then you can tell me what y is. So y only depends on x. That's why we say it's a function of x. And so if we try and draw this, I could draw like a little, we'll call this a tree diagram later, but we're saying in order to know y, you have to give me x. You give me x, I'll be able to give you y, all right? Pretty simple. And if we have that, then if y depends on x, then we can talk about the derivative of y with respect to x. Now let's take a look at another example. If y is equal to x squared and x is equal to sine of t, then find dy dt. So this is saying if I change what variable a little bit? T a little bit, then how much does y change, right? Well, if I change t a little bit, it's gonna affect this, right? And that value is x. So if I change t here, this thing does something and it changes x. And then that change in x, in turn, has an impact on y. So it's like y depends on x, but then x also depends on t, right? So how would we differentiate this? How could we find dy dt here?
Plug in sine t for x.
You could replace sine t, right? In for x. So let's just do it that way. If we replaced it, it would just become sine, what, t squared. And now that's equal to sine square t. That's another notation for it, right? And now it makes sense to talk about dy dt. we just take the derivative of this with respect to t, and that would be chain rule, right? We have to do 2, and then sine t, and then times the derivative of sine, which is cosine t. And that's actually a double angle identity, but who cares? I mean, that would be our chain rule, right? We all agree? But I want us to look at it a different way. So in that problem that we just did, notice that y was a function of x, and x was I'm not going to call it f, I'm going to just call it x is some function of t. Then y can be determined if we know x, and x can be determined if we know what t is, right? So y ultimately depends on t. You give me t, you give me a little change in t, and I can determine the change in y. So visually, it looks like this. Y depends on x, but x, so I have the idea of a derivative. And then I also have, I also have that x depends on t, and so therefore there is a derivative between these two, right? There's a rate of change, t changes a little bit, x changes a little bit, x changes a little bit, y changes a little bit. So why am I telling you all this? Because algebraically, if I write dy dx times dx dt, essentially these things are gone, aren't they? Do you all see that? And this is the same as dy dt. But look at this expression. Dy dx times dx dt, isn't that just whatever this derivative is times whatever that derivative is, right? So let's go back to that previous problem and let's do it this way instead. You'll see what I mean hopefully when we do the problem. Okay, so I have that y is a function of x, so what would dy dx be? 2x, okay? And then I have that x is a function of t, so what would dx dt be? Cosine t, right? And according to what I just said, dy dt should be those two multiplied, dy dx times dx dt. Now what's dy dx? 2x times dx dt, cosine t, and that isn't quite the answer that we just had, right? But we can replace x with what? With sine t, and then we get the exact same answer, don't we? Y'all see how that worked? So if we can establish the relationships between one variable to the next, and then talk about the derivatives, down that line, then the chain rule is just multiplying all those derivatives together. At the end, yes, you may have to plug some stuff in, but it makes it a little bit easier as we proceed through, as what we're going to do now. Because we're going to have more than one variable, so how do we keep track of everything? All right. That's the chain rule from calculus, basically. How about this one? So this should remind you of something we've already done, right? This is something we just did in the last few days. We have that z depends on two things, right? X and y. So this is basically a surface, isn't it? I mean, you could look at this as like f of xy equals that, right? So we have a function of two variables. So if I change y a little bit, is that enough for you to tell me what happens to z? If I make a little change in y, is that enough for you to tell me what happens with z? Okay, so why or why not? What do you think?
Because z depends on x and y.
Yeah, because you have to know x and y, right? So the only way to know how much z is going to change if I change y a little bit is if I promise you I'm not going to move x, right? If I hold x constant, then a little change in y will have an impact on z. Or you can do it the other way around. If I change x a little bit and hold y constant, then yes, I can talk about the change in z. Does that make sense? So we did these two partials in class already. Let's go ahead and do them here. Okay, let's do them. Let's do them, and we're going to talk about how we're going to use like this little diagram to do it instead. So for this, notice we use the partial, right? That partial symbol instead of the d. Partial of z with respect to x. What would that be here? So what am I holding as a constant? Y. And so to take the derivative of that, I'm going to have to use which rule? Product rule, right? I have a product right here. So I do derivative of that, which is 1 times this, plus the derivative of this piece, right? Here's my product. What's the derivative of sine of something? Cosine xy. And then chain rule says then we have to go inside and take derivative of what's in here with respect to x. So hold y constant. What would that be?
Y.
Just y, right? And then finishing off the product rule, we then have to multiply by the first function, which was x. So that's the way we would have done that last class, right? We all good with that? Now, there's another derivative we could have found. That would be the partial of z with respect to y. And this time we hold x to be constant. That's nice, right? Because then we don't have product rule anymore. If x is a constant, then we don't have to do product rule. So the derivative of this will be the x, which is constant, just comes for the ride. Derivative of sine of something, that's still cosine, right? But now the derivative of the inside with respect to y would just be just x, right? Because that's like, this is like taking derivative of 2y, which would be 2. We all clear with that? Yes? Sure. That x could go out there, x squared, yes? Okay, now, so we've done that. There's nothing new there. What's new is the way I want you to now visualize this. So let's say that z, if we have z as a function of two variables, then z can only be determined if x and y are known. So z depends on two things as opposed to one thing. And therefore, there are two possible partial derivatives. And so it looks like this. We have z depends on two variables, and therefore when you talk about the derivative between these two, it's no longer that d, right? It's partial. And the reason it's partial is because z also depends on another variable. Understand that difference between that and when we have this? This you can say dy dx because y only depends on x. So I call this like a straight derivative, like a straight up derivative, and here's your partial derivative. So we have that partial as possible, and then we have that partial as possible. So two possible partial derivatives. Whoa. Okay, so this is where I had a little problem with my notes. Don't save this. I have to go to more static one. Okay, so let's look at this example here. Oh, wait, that's one we just did. Oops. So let's look at this one. That's a little too big. Okay, so let's see if we can't get our heads around what's going on here. And I'm going to start at this point drawing these things we call tree diagrams. All right, so ultimately z depends on x and y, right? We just did this a second ago. But now I'm adding to this that x is also a function of t, right? And the y is also a function of t. Understand? So if I draw this, I have z depends on x and y, right? And then x depends on t and y depends on t. Make sense? Now you see our bottom row here has t in both of them. So if I change t a little bit, that impact will be felt through the x and y separately, and then that will impact the z, won't it? So a little change in t is all I need to talk about a change in z. Does that make sense? Doesn't matter that these are two branches, because t will impact both branches, and then both branches will go up and impact the z. See, when that's not there, then a little change here depends on this, and then a little change here depends on that. Do y'all see the difference? So let's draw what derivatives are possible. So from here to here, what is that derivative?
The
Partial z with respect to x, and then the derivative from here to here is dx dt. Why am I using d and not partial?
Because there's only two.
Yeah, because x depends on just one thing, right? And then I'm doing the same thing here. Partial z with respect to y this time, and then down here dy dt. So how many, well, I can't ask you this question because it's already up here. I'm only asking you to find one thing. I want to know how z changes if I change t a little bit. And this question makes sense because of what I just said. Z will change just a little bit if I just change t. So I can ask about this. Now, what do you think it is? What do you think that is? Looking at all this tree here, what do you think the formula for this is going to be? Any ideas? Take a guess at it here. What did we see earlier? If we just had like if we had one path, it was just these two multiplied, right? So what do you think if we have two paths? Just add them. That's it. So you're going to go this times this plus this times this, and that's going to be what the derivative is. That make sense? So I'm going to go partial z with respect to x times partial x with respect to t plus partial z with respect to y times dy dt. And that is the formula that we're going to use to figure out what dz dt is. Any questions before I erase this part of the tree here? We're good? Okay, let's do these derivatives because each of these is going to be a little bit of work. So let me get these. I need 4 derivatives now, right? 2 of them I did in the previous example. What was the partial of z with respect to x? What was that, like sine xy plus cosine xy times y times x? So I'm going to go xy cosine xy. That's if I would have just moved those factors out front. So that's partial of z with respect to x. Okay, I need the derivative of x with respect to t. So I come up here, I look at where I have my equation with x and t. I differentiate that with respect to t, just 2t. I need the partial of z with respect to y, which we did in the previous example. That was just x cosine xy times x, right?
Yeah.
So I'll just put x squared out here. Then dy dt. And then that would be what? 1 over t. Yeah, 1 over t. Okay? So now, let's come over here and let's put the derivative together. The derivative of z with respect to t is going to be, I'm going to run out of room, but let me go for it. It's sine of xy plus xy cosine xy, all of that, that's just this, times 2t plus x squared cosine xy times 1 over t. That's it, right? Now, we want our answer in terms of t. So that means now you go in here and you replace all your x's with t squared plus 1, and you replace all your y's with natural log of t. And that will be your final answer. It's going to look ugly, but, you know, that's just the way it goes. Can you all appreciate that? Can you all appreciate that? Let me just remind you, had we not done it that way, so do I have to go replace all these? No? Are you all okay with that? And just put like, right there you'd put t squared plus 1 in parentheses times natural log of t, and then t squared plus 1 in parentheses natural log of t, t squared plus 1 in parentheses natural log of t, 2 times t, leave that alone, and then, you know, replace your other x's. But had we not done that tree, and just in the very beginning of the problem, replaced the x and the y here with those, right? Then we could have differentiated this. We could have, right? It's just, you know, you have what? Like product rule there. When you're doing product rule, you're going to have a chain rule on this, but inside that chain, you're going to have product, right? It just would be, I mean, it can be done, right? But it's just, I think the tree is a little bit cleaner because your derivatives are cleaner, and then you're just putting them together at the end. And whatever you get here is this. It's the same answer. So that's what this note is saying. Oop. That's what this note's saying. It's trying to say. Is that, sorry, I can't go any further there. It's saying when your function, I guess the one at the top of the tree, when that function depends on exactly one variable at the end of the tree, then there's only one derivative possible, and that's dz dt. And it would, in this case, be it's the sum, you can look at this right here as the sum, right, of the product down the branches. That's what it is. So what do you think we do now? We just start getting crazier and crazier with this, okay? So imagine now we have that same z is equal to x sine of xy. So z depends on x and y, right? But now look at x and y. What do x and y depend on?
S and T.
S and t. Not just t, s and t. So if I draw a picture, I've got z at the top, right? I've got z depends on x and y, but x depends on s and t, and y depends on s and t. See that? And so now let's just go down the branches and talk about what derivatives are there. So down this branch, what's that derivative down this branch? Partial z with respect to x, right? Now what about this branch? Partial x with respect to s. This branch? Partial of x with respect to t, right? Now here, partial z respect to y, right? And then here, partial y with respect to s, partial y with respect to t. Now let's think about this. Z, at the end of the day, z depends on how many things?
Two things.
Just two things, s and t, right? So since z depends on two things, that means that there are two derivatives possible, right? This goes back to what I drew earlier. When we had just this picture, we said that there were two possible derivatives, the partial of z with respect to x, partial of z with respect to y. Now, if there's a chain of events happening between, it doesn't matter what's happening in here, if at the end of the day there's two variables down here, then I can only ask for two derivatives. I can ask for partial z with respect to s, partial z with respect to t. Those are the two things I can ask for. We can ask for, okay? So if you change s just a little bit, how much does z change by? But we're holding t constant. Here it's the opposite. We change t a little bit, how much does z change? But we're holding s constant. So how do you think we get this first one? How do you think we get the partial z with respect to s off of this thing?
Would it just be partial of z with respect to x times partial of x with respect to x?
So this, oh there it goes. This one, and then what?
Times the partial of x with respect to s.
this one, right? We go down that branch and that branch only. And then add it to this one down this branch. Make sense? The reason why these don't factor in is because if you think about it, if t is being held constant, right, then this derivative is 0. Does that make sense? Like, this is basically nothing happening here. So you could, if you wanted to, imagine that you're actually going down all the branches, but when you come down this branch, if you're holding t constant, this is 0, so it's going to kill off one of your little pluses, and it'll be zeroed out. That make sense? Okay, so here it is. It's going to be partial z with respect to x times partial x with respect to s plus partial z with respect to y times partial y with respect to s. Now, I don't think I want to go through and calculate all 4 of those again, because we've already done this one and this one now twice already, haven't we? We've looked at it. But these 2 we haven't done. So is it all right if we just do those, and then you could fill it all in later? Okay, so this right here would be what for us?
4.
Just 4, right? It's the partial of this with respect to s, which means we hold t constant. Derivative goes to 0. Derivative of 4s is 4. So that's just going to be 4. Then plus this one we already did. How about this one? Partial of y with respect to s. Yeah, we're going to have derivative of natural log of something is 1 over it. So basically we're going to have 1 over st, but then times derivative of what's inside with respect to s, which would just be t. And the t's cancel, and you just get 1 over s. So this would be 1 over s. And then all this junk in here is the same expressions we had earlier, right? Like whatever it was, like xy cosine xy, and then this one's like x squared cosine xy. Then you have to replace all your x's with and your y's with and then it would look ugly, but that would be it, okay? Are you getting the idea here? And you can imagine that you could just keep going with this, right? And your tree could just become as crazy as you want it to be. Yeah? But it gives us a nice, clean, I think it's a clean way of taking derivatives where you don't actually have to take all these and plug them in and then go after the derivative. You can do them kind of separately. Okay. So the general case. See if we can make any sense out of this. Let's say that we have z, right, is some function, I'm going to say it this way, z is some function of x1, x2, x3. Let's say that you have that z is a function of n variables. So instead of using x and y, I could have a lot of them, so I'm going to start using subscripts. So I have z is a function of n variables. Let's say that x1 is a function of s1, s2, s3, right, sm. Variables. What I'm trying to do is generalize this, and it's hard to generalize. It is very difficult to generalize this. I think that's why the tree is so important. Let's say that x2 is also a function of those same m variables. And I do this all the way through xn. Notice I'm using m, and n because those don't have to be the same number. What would our tree look like in this case? we start out with z, right? And z would have how many branches off of it? N of them. So you would have x1, you would have x2, right? x3, and a bunch of these, right? And then you get to the very last one, x sub n. So there's a bunch of branches in here, right? And then each of those branches has how many branches off it? Yeah, m of them. S1, S2, right? Sm. Every single one of these has that, right? So how many derivatives are possible?
Infinite.
M of them. M. Because z can change, right? Z, a little change in S1 isn't enough for you to tell me about z. You'd have to hold all of those constant, wouldn't you? So that's one derivative. It would be like, go down x1's branch, that would be a partial, right? Partial, partial. Multiply those together, plus, go down the next branch, partial, and then go to S1, another partial, then plus, and you go down all those branches. That would be only one of the derivatives possible, right? Do y'all get it? So one possible derivative would be partial z with respect to S1. Another one would be partial z with respect to S2. And we could keep doing that, and we could do, last one would be partial z with respect to Sm. So there would be m possible partial derivatives for this. Understand? Now, what if I added one more thing to this? So I want to erase this. What if I added one more little element to this, and I told you right now that S1 was a function of t and w, and S2 was a function of t and w. And I kept doing that for all of them. Then that means off of these branches we have what? TW. Off of that branch, TW. And so how many derivatives are possible now? Just two, right? The only two that we have are what? Partial z with respect to
Or T or W.
t, or we could have partial z with respect to w. So there, all this n and m didn't matter anymore because at the end of the day, we only had two variables that everything depends on. So there's only two partial derivatives possible. Make sense? Okay, I'm trying to generalize, but it gets messy, and you could, what if, yeah. What if it just depended on, what if all your s's depended on t? Then what's the only derivative possible?
Partial Z over partial T.
Is it partial?
Oh, D over.
It would just be dz dt. Because ultimately, we don't have to hold anything constant ever.
You just go down the branch.
You just go down every single branch. So like if this was t here, we take that out, take that out. So you just go down this branch, plus that branch, plus next branch, next branch, next branch, plus next, and go through all these, and it would be a mess, but this is how this generalizes. So I hope that makes sense. Okay, so now let's take a look at some special cases. Sometimes this tree can be a little bit tedious, and so let's take a look at some special cases here. So let's say that we have a good old-fashioned z is equal to a function of two variables. All right, so this is like a surface. Then, because this is given to us, z is a function of two variables, we can always move this to the left-hand side, and then we get this equation, wouldn't we? And so if I define this left side to be capital F of x, y, z, then you can look at the left side of that as being a function of three variables. I'm calling it capital F. So capital F is now defined to be the left side of this. then f is really a function of 3 variables. Also, x and y may depend on each other. So we're going to set up this equation and differentiate implicitly. Just follow me through on this, all right? I think I'm showing this to you, you're probably freaking out when you first see it. But we're going to differentiate implicitly. And let me see here. I don't want to do this. I'm wondering if I want to do an example first. So f depends on what things? Okay, x, y, and z. Right? X, y, and z. Does that make sense? That f would depend on that? So, and then it also says here that x and y may depend on each other. Now, what does that mean? Not directly this way, down. So, like this, like that, like x may depend on y may depend on x. And then what does z depend on?
X and Y.
X and y, because z is a function of x and y. So you have something like, I know this looks crazy. Okay, doesn't that look kind of nuts? All right, so let's look at the next note and let's see what we're basically going to come up with a formula for this. So let's say that we want the partial of z with respect to x. So we're going to differentiate both sides implicitly with respect to x. So I need to bring up that equation back up here. Well, we can just do it right here. I think we can just do it right here. Yeah, let me try this. Let me do this. This will make, I think, see, what we're trying to do is come up with this. This right here would be partial f with respect to x, right? That'd be that. And then x down, let me go it this way. I'm going to do it this way, like this, and then I'm going to do 2 branches here, x, y, and then x, y, something like that. This is kind of ridiculous to say x depends on x, but it's not wrong to say that if I knew x, I would have x, right? If someone gives me x, I know what x is. So how many branches do we have here that we could go down here and then down this, right? And this would be partial x with respect to x, which should be 1. And then we have this way right here, partial f with respect to, x, right, with respect to y. I'm going to run out of room here. Partial y with respect to x, partial y with respect to y, partial z with respect to x, partial z with respect to y. Okay. So let's see where this is coming from here. We have partial f with respect to x. That's down here, here, right? Now what about the next piece? I didn't put these in here, damn it. Partial f with respect to y, partial f with respect to z, right? I forgot to put those 2 in. So what's the next piece right now? It's this one right here. We're going to go down this one and then that one right there. Okay, so we're going to add those 2 together. That's this. And then the last one would be this one and then going down right here. Yes? And that, so if we're holding our y constant, then we're not going down the y branches, we're going down the x branches. Make sense? And so this times this plus this times this plus this times this, that would have to be equal to, so I basically differentiated the left side and got this off my tree. Differentiating the right side, I get 0. Therefore, we can try and solve now for the partial of z with respect to x, which is just right here, this guy right here. So you just move things around. So, you know, move things over, right? And then divide, and I think you can probably algebraically convince yourself of this. All I want us to really know is that there's a formula for this, all right? There's a formula. We'll use the formula. The derivation of it's not important. This is what's important. So if remember where we started. If somebody gives you z is a function of x, starting with this, and we want to know the partial of z with respect to x, then what we can do is we can move everything over to one side, call that capital F, right? Capital F. Take the derivative of that with respect to x, partial derivative of that with respect to x, over the partial of that f with respect to z, and figure out what that is and put a negative in front of it. That's how we can find that partial. Now, there's two partials possible, right? You could do partial of z with respect to x, or you could have gone down the y branches. I believe this is highlighted in red because in the notes it's a typo. So if you have the notes, just make sure you change that because I'm pretty sure it's a typo there. So if we go down the y branches instead, we get a different formula, don't we? I'm not going to go through it, but if we go down the y branches, we get this formula. It looks very similar. The only difference is this, right? So let's see this in action. And maybe we can look at this and appreciate the power of what we were just able to derive. Right now, this does not look like z is a function of two variables, does it? We cannot easily solve for z, can we? No. But we can use implicit differentiation to find both of these. So let's do that first one. Partial of z with respect to x should be equal to negative partial of f with respect to, what was it? X over partial of f with respect to z. So that's the first of the two formulas I gave you, right? That's this one right here. We're trying to find the partial of z with respect to x. Here's our formula. All right, so first we need to figure out what the heck is capital F. So what's capital F? It's this equation with everything moved to one side. That's what it is. All right, so all we have to do is move that 1 over, and that's capital F. So to make things easier for me, I'm going to put that to minus sign, put equals 0, right? This right here, oh, not the if. That right there is capital F of x, y, z. Okay? Understand? Now, to calculate this, I need partial z with respect to x. I'm going to go negative. Now, what is the partial of capital F with respect to x? That means we're going to treat y and z like constants. So what is the derivative of this with respect to x? 3x squared. 0 plus 0, right? Plus 6yz. Right? Because x is the variable, everything else is held as a constant. So that is the top. And now what about the bottom? Partial of f with respect to z. So now we treat z like the variable and treat everything else like a constant. So what would we have there?
3z squared.
3z squared, and that's it? Plus 6xy. Wasn't that nice and clean and easy? Do you agree with that? Okay. Let me show you, well, yeah, what I'm trying to figure out is, yeah. What that formula is allowing you to do is not have to create a tree off of this. You're not having to do f x, y, z. X depends on itself and possibly y. Y depends on x and possibly itself, and z depends on both x and y. It's basically stopping you from having to do this thing. And we've already done it in general, and we came up with a formula for this, and that's what it is. So if you don't believe it, you could go make your tree, do all the products, go down the branches, simplify it, and it's going to simplify to be this. So this is a lot faster. Understand? But it allows us to find the derivative of something we can't solve for z. Like we couldn't really solve that for z earlier, but we can still see how much z is going to change if I hold x constant. So it's nice. Now what about the other one? The only difference between these two is that top one right there, right? And do we have a negative sign also? Yes, okay. I thought I had a typo in this, and I'm pretty sure I fixed it. Anyone have a book? No? Nobody has a book?
I have a book.
With you?
Yeah.
You mind breaking that out real quick? Just want to make sure that I have the correct formulas up there, because I know there was a typo. I'm pretty sure I fixed it a few semesters ago, but I haven't done the Cal 3 in a while, so I just want to double check. Oh, this is used. If the spine falls off of this, I'm not going to claim that it's my fault. Yeah, these are on page 655. Yeah, okay, they're correct. All right, so the only thing that would change in the second one would have been that partial on the top one, right? We would have gone with respect to y instead of x. All right, so this section, I think we're pretty much at the end of this. Yeah, that's it for this section. So on this section for the homework, it's just practicing. You're just going to be doing, some of them it's going to ask you to draw some, tree diagrams and then calculate certain derivatives. So you have to go down the branches. And then towards the end, they say use these formulas to do problems like this. So very computational, nothing real crazy here. Questions or anything? So this course just continues to be just random, seems random, like we're just all over the place, right? Doesn't seem that way? Yeah, that's kind of the way it is. We are headed for an ultimate goal here. I think we're about one section away from putting a lot of this stuff together to start to be able to do some nice things, all right? But we have one last sort of piece of information that we need to get straight. And this is really an important section. It's called the directional derivative in the gradient vector. Here we go. So let's take a look at this surface. I'm about to show you a surface. And here it is. So here's a surface. And I've shown you surfaces in the past like this, and I haven't told you that this is the actual surface. Sine of x minus y plus cosine x. I can change that surface to a couple of different ones if I want to, but let's stick with this one for now. So do you see that I've picked a point on that surface? It's this black point right here. I made it real big so we can see it. All right, so that's us standing on the surface, right? Now what we've already talked about is that if we were standing on that surface and we kind of aimed ourselves parallel to the x-axis and then talked about a slope of a tangent line there, that would be our partial derivative with respect to x, right? So visually, we've seen this. What we're doing is we are slicing it with a plane that runs parallel. Here's our x-axis coming at us. So we're running parallel to the x-axis. We're going to walk along there, and as we walk, we will have a tangent line that changes as we move along that curve, but as long as we stay parallel to the x-axis, we're going to have some slope, right? All right, so that's, again, not new at all. We could have also pointed parallel to the y-axis, which would have put us there, that way. So see how it changed? And we have the concept still of a tangent line that way. But what forced us to do, like, why do we have to point that way or that way? Why are all the other directions off limits? Well, they're not, okay? We can point in any direction we want and talk about a slope of a tangent line in that direction. And this is where we get the idea of this thing called the directional derivative. It's the derivative in an arbitrary direction. So what we want to imagine now is taking that plane. Let's start back at the x-axis. This might be just a little bit too big. There. Okay, so now starting at the x-axis, just imagine that I rotate this plane just arbitrarily. You know, so let's say we go, aim it that way, right there, and just start walking. You know, we're gonna have a tangent line in that direction. So the way we're gonna do this is just imagine again that you're standing on the surface, and let's say you can see through the surface to the ground below you, right? Down on the ground, imagine a point. And at that point down on the ground, imagine an arrow pointing in the direction you're pointing in. So that's what this red thing is on the ground. You see that one right there? If I look from straight above me, do you see that that red is pointed in the same direction I'm pointing in? Now that red thing on the ground is a vector, and vectors have direction, right? So imagine that vector on the ground. It's two-dimensional. I'm sorry, it's not coming up z, it's just always in the xy plane. And since it's a vector, I can slide it to the origin, it's the same damn thing, right? It's the same direction. So I just have a copy of itself over here, so that if you look at it from the top, right, let's look at it straight up from the top. Stop doing that. Then, as I change my angle here, okay, I'm kind of backwards. Need to go out my x-axis. Come here. Stop it. I don't know if I'm able to get this. There we go. Okay, so that is me pointing out the x-axis, right? So I have the vector going out this way. If I rotate and I'm parallel to the y-axis, I'm there, and then anywhere in between, right? Like that. All right, so how do we actually calculate the slope of the tangent line in an arbitrary direction? And that is the next formula. So if you are given a function of two variables, a surface, then f has what we call a directional derivative in the direction of the unit vector u, which is two components, a and b, right? So this is, I've capitalized unit vector because I told you when we look on the ground we see an arrow down there, and that's a vector. That vector that's down there, we need it to be a unit vector. Unit means what? Length of 1, okay? So if somebody tells us the direction we're supposed to point in terms of a vector, we have to first make it a unit vector. Once it's a unit vector, we can use this formula to find the slope of the tangent line. And it is written this way, capital D, which means the derivative, okay, in the direction of u. So it's subscripted with that little u vector, of the function of function f of xy. So this is your directional derivative in the direction of u, is equal to what? A, which is just the first component of your unit vector, times, what is that? The partial of f with respect to x, plus b times the partial of f with respect to y. So basically what you're doing, it's kind of like this. We know how to do this, right? That's partial of f with respect to x. We know how to do that. That's partial of f with respect to y. If I want to point out in that direction somewhere, then I'm just going to scale this by something and scale this by something, and that's going to give me the slope here. And what we scale it by is what? Just the components of the unit vector. I think this is pretty amazing because think about it again. Let's say we have a surface. Let's say this is x and this is y. We have some surface here, and I'm here. And let's say I want to point in the direction of the x-axis. Okay, so I want to point in the direction parallel to the x-axis and walk and find the slope of the tangent line. We've already done that, right? We've already done that? But this formula would still work. because what would be my direction vector on the ground? What would be the unit vector that would be pointed down the x-axis? What's that vector? It's the one, so it's two-dimensional. It's on the ground. So it's the vector pointed down the x-axis. 1, 0, right? 1, 0. And that means that A is 1 and B is 0. And if you go in this formula and you put 1 here and 0 here, this is gone. You just get the partial derivative with respect to x, which is what we said it was, right? Now, if you point the other direction down the y, right, then the vector down this direction, unit vector down that way, is the vector 0, 1. And that changes places. That goes away. Now you're just looking at partial with respect to y. Any vector pointed in any other direction is just some combination of those. Does that kind of make sense? So this is actually a more general formula than the ones we started with. So the answer that we get from this is a number. And it represents the slope of the tangent line to that surface in the direction of that unit vector. I believe an example is in order. All right, we have a surface. Z is f of xy, which is this polynomial, right? Find the directional derivative at the point 1, 2 in the direction of a vector making an angle pi over 6 with the x-axis. So I'll try and illustrate this. I'm over here at the origin. I want to go xy, right? So I want to walk out. Let's say the origin's right here because I want to kind of stay on camera. So I'm going to walk out x direction 1, right? I'm going to walk out y direction 2. I'm going to get plugged into the function and go somewhere, up or down, right? And I'm now standing on the surface. And now what I want to do is I want to point myself in a direction that makes an angle of pi over 6 with the x-axis. So remember, I'm standing here on the surface. Here's the origin. Here's the x-axis. Pi over 6 like this. Okay, so a little rotation this way of pi over 6 is where I want to be pointed. So when I'm over here, I just imagine pointing parallel to the x-axis, rotating pi over 6, and then I take a step. And am I going up or down? What's the rate of change? Understand? So here's what we need. We need the directional derivative in the direction of the vector u of the function f of xy, right? That's what we need. Now, do we know what the vector is? We don't know it. It wasn't given to us, was it? So I can start by maybe looking at my domain, which is the ground, right? My vector needs to be making an angle of pi over 6, right? And it needs to be a unit vector. It needs to be a unit vector. That's okay, it's safe over there. That needs to be a unit vector. So can you give me a unit vector there?
1, 1. Or, yeah, 1, 1.
1, 1 would be pi over 4. I mean, right?
0, 0. No, it would be, wait, why would 1, 1 be pi over 4? Pi over 4 would be root 2 over 2 and root.
Yeah, but the ratio, when your ratios are equal, then you're at 45 degrees, right? Like if this was 1 and that's 1, then you're at 45 degrees.
Oh, okay, I see what you're saying.
So the vector 1, 1 would be 45 degrees, but it also wouldn't be a unit vector. Root 3 over 2, 1/2. That's basically the point on the unit circle at pi over 6. That's all it is, but written as a vector. Do y'all agree? So this is my AB. Right? That's my AB. Now I also need some other things in this computation. Maybe I should write the formula here again. It's A times partial of f with respect to x at xy plus b times the partial of f with respect to y at xy. So I need to get these partials, don't I? So let's do some partials over here. What is the partial of f with respect to x? Let's see, 3x squared minus 3y. That's it. Okay, what is the partial of f with respect to